We're doing question number 23 in chapter 9 on page 268. We've got this horizontal rod being supported by this rope. It, the rod, pushes into the wall, which means the wall is going to push up and out. So there's our force diagram. That's listed in the book like that. We've got to find the tension and the force for the. We've got two questions to answer. We've got to find the tension and the force for the wall. So, there's a couple different ways to approach this. Again, remember, we have our three conditions for equilibrium. Sum of the forces in the x equals 0. Sum of the forces in the y equals 0. Sum of the torques equals 0. And oftentimes we have to use multiples of those things because we have to find out, more than one thing, right? So we have two unknowns. So we know for sure we're going to have to use at least two of these forces, or two of these, equations up here. And as it turns out, in reality, we really got to use all three. So, you can do whatever you want in terms of an order, as long as you have the physics correct, right? So I'm going to choose, because I know from history that using the torque one is often the easiest because we can eliminate things that we don't want. So if I want to use the torque thing to find tension, I could set this as my pivot point. And that way I don't have to worry about this wall force at all. I only got to worry about this. So let's do that. So the sum of the torques is equal to 0. Now I've got a torque because of the tension. So I'm going to call this torque because of the tension. Wants to make this thing rotate counterclockwise, and this weight wants to make it rotate clockwise. So minus the torque because of the weight must equal 0. Now the torque because of the tension is the full tension force times the sine of 50 degrees, because only tensions at right angles, or only forces at right angles, create torques. And we have to multiply that by the length of the beam minus the weight of the object. And the weight of the object happens to be, what, 30 kilograms. So that's m times g times the distance here, which is L over 2. And that must equal 0. So, then Ft sine of 50 degrees times L must then equal mgl divided by 2. If I get rid of the L's and divide over by the sine of 50 degrees, then Ft happens to then be equal to mg divided by 2 times the sine of 50 degrees. And if we plug our numbers into there, then that tension force, that's the full tension force now, becomes roughly 190 newtons. It's roughly 190 newtons. Now, there's our answer right there. Now, to get this wall force, in reality, we're going to have to get its x component and its y component, and then put those things together. In order to get its x component, we're obviously going to use this sum of the forces in the x, and to use its y component, we're going to use sum of the forces in the y. So sum of the forces in the x is equal to 0. So we've got the wall's x force minus Ft times the cosine of 50 degrees, because that's the x component, has to equal 0. So F of the wall in the x is Ft times the cosine of 50 degrees. So the wall's x force is 190 newtons times the cosine of 50 degrees. So the wall's x force is then roughly 123 degrees. Or I'm sorry, 123 newtons. Same thing for the y force here. Sum of the forces in the y must equal 0. Well, what's acting in the y? Fty plus the wall's y force minus the weight of the object has to be 0. So then the wall's y force, Fy, force of the wall on the y, will be equal to m times g minus Fty. So the wall's y force then is m times g minus this full tension force here of 190 um, times the sine of 50 degrees. And if we put all those numbers together, then the y force for the wall is roughly 147 newtons. All right. Now, how do we get the actual y force? That's going to be this squared plus this squared, square rooted. So the wall's actual force will be the square root of 123 newtons. And I've got to square that plus 147 newtons. And I've got to square that. So the wall's actual force then is roughly 190 newtons. Now, what angle is that thing? Well, we could use sine, cosine, or tangent. We can use whatever it is, that we want. So if we came back up here, right, if this is F, the wall in the X, and this would be, F wall in the Y, and then this is my wall force right there. This is going to be some angle, it's going to be some angle theta. So I've got 123 and I've got 147. The 147 is the opposite side and the 123 is the adjacent side. So tangent is equal to opposite over adjacent. So, the tangent, if I want to do that down here, the tangent of theta is opposite over adjacent, which is going to be 147 newtons divided by 123 newtons. If I get that tangent, that's going to be 1.19, and then therefore the angle, as dictated by that, would be about 50 degrees. So this wall's force is roughly 190 newtons at 50 degrees, above that horizontal.